Hi and welcome to MSc. In this video we're going to be looking at an example of the binomial theorem expansion. So let's look at how to expand 3a plus b to the power of 5. And of course to do this we're going to use the binomial theorem as it's written out here in a general form. What makes this example a little bit different than some other examples is the fact that we have a coefficient on the 3. Again, this a and b don't always just have to be a and b as separate individual variables. They can have coefficients and nuance to them as well. So we have to figure out how to deal with that. So it makes it a little bit more than just completely just subbing in without having to give it a lot of extra thought. So let's look at this. We have 3a plus b to the power of 5. And so the first term we know is going to be the n choose 0, right, where we're choosing none, and the b value is still has an exponent of 0 in this case, and so it's going to start off as just our a to the power of 5 because that's our n value. This is going to drop down there. Notice I've included the 3 and it's in brackets. It has to be in brackets. The next part of this expansion is n choose 1, so 5 choose 1, which is 5. Again, from that n equals 5 row on Pascal's triangle. I know that my a value here is going to start counting down on the exponents, where my b value is now going to start to count up. So it has an exponent of 1. Then the next coefficient is going to be 5 choose 2, and I can do that in 10 ways. And then I'm going to have 3a, and it's going to be to the power of 3, and my b is now going to be squared. Then I'm on to the next one, which is also a 10. This is 5 choose 3. And this is going to give me an 3a squared times b to the 3 plus n choose 4, which again is 5. And this is going to give me 3a times b to the 4. And then at the last term, we're n choose n. So 5 choose 5, which is only one way to choose all of my options. Again, because the order in the choosing doesn't matter. And the b is just going to be raised to the power of 5. So we've really done the expansion here, but we haven't fully simplified. So that's what we need to go back and do at this stage. So this exponent applies to both pieces inside. That 5 sees both things. So 3 to the power of 5 is 243, and then we have a to the 5, and then we're going to have 5 times 3 to the power of 4, which is going to generate 81. We're going to have a to the power of 4, b, and then it's 10 times 3 cubed, which is 27, and then a cubed, b squared, plus 10 times 3 squared is 9, a squared b cubed, plus, and this is an exponent of 1, so it's 3 to the 1. I can go ahead and make that multiplication right now of 5 times 3, a b to the power of 4 plus b to the power of 5. So the way I dealt with this coefficient of 3 is I brought it along, put it in brackets, and then I went and simplified with the exponent on the outside. And where it was suitable, I did another multiplication with the coefficient out front. So now let's go through and clean up the last little bit of the multiplication. So there's nothing to do with that first term. The next term, it's 5 times 81, which is 405. a to the 4b. 10 times 27 is 270. a cubed b squared plus 90, which is the 9 times 10, a squared b cubed plus 15, a b to the 4 plus b to the power of 5. So now this is fully expanded. I can't collect like terms here at all anymore because I have no other a to the power of 5 term or any other term that's a cubed b squared. One thing I like to do at this point is I like to make sure that my exponent patterns all match. I start with a to the power of n, which is 5 in this case. I end up with b to the power n, and all my exponent totals should add up to this 5 value here, right? So 1 and 4, 3 and 2, 2 and 3, 1 and 4, and of course the 5 and the 0 that we don't write. So that works. But notice here, because of the 3 coefficient on the A, I've lost my pattern from Pascal's triangle. It's no longer visible as it was here with a 1, 5, 10, 10, 5, 1. So that's something to watch for when you have coefficients on one of your two variables. I hope this short run through of an expansion using binomial theorem has been helpful. If it has, please consider liking the video and subscribing to the station. And as always, thank you very much for listening and watching.